measurements within people. It could be, could be randomly selected villages, people within villages, times within people. We haven't seen a lot of that. We'll see much more of that in mixed models, but you can have hierarchical structures where you want to start modeling how that hierarchy affects the outcome. And I just talked about this, like the design questions. I think I'm going to have a little thing more in design where we talk about like how to do sample size calculation with repeated measures. Get a little more complicated than if I have cross-sectional data. In this case, we really talked about like an optimal situation. How would you want to measure things given the things you want to study? And so that's the same thing. Then I just pointed out the first thing that we come back to over and over again. This is a regression course for the most part. We're talking about how to do regression for longitudinal data, how to make inferences about certain associations, et cetera. There's lots of different forms of regression. We're really concentrating on these generalized linear models, linear, logistic for binary, and Poisson negative monoidity for counts. They all have this form. Again, we're always modeling some function and some transformation of the mean is a linear function of covariates. And again, they don't have to be just x1, x2. It could be x1 plus x1 squared plus x2 times x1. It could be complicated. But it's some linear function of what we call basis functions. Those are just things you make out of the covariates in some way. And H is called the link function. I'm not expecting you to memorize that term, but that's just how you transform it so it's a proper model. So if I have a binary outcome, the transform is xbit. If I have a linear continuous outcome, it's usually just identity. It's just the y is equal to the linear function. Poisson, we use log linear. All those result in proper models, meaning that the prediction will fall into the natural range of the random variable. So linear, there's no you can add constraints. I haven't talked about that yet, but typically there's no constraints. It could be minus infinity to infinity. Logistic can only be between 0 and 1, and Poisson has to be 0 or greater. So, and then just a brief summary of that statistical roadmap, just sort of the optimal kind of sequence of steps you would take if you're doing this from first principles. And at least in our program, biostatistics, particularly when you get into more advanced courses, we teach this over and over and over again. And again, I try to talk about specifying this first and not having that come after you fit your model, right? You choose what you're interested in beforehand, make your model such that it fits the data well, and then estimate that parameter from the resulting coefficient. So that's one example of this kind of roadmap, as opposed to fitting the model and saying, okay, this is what I'm reporting now. Never good practice. Then we did notation. And again, I'm not really going to be a stickler for notation. I may ask notation questions, sort of like I did at the end of the chapter, where we had examples, like this is a study, here's how we're measuring things, give me an example of the data. And using the sort of way we use notation to represent the outcome and the covariates. So again, there's reasons why we do that. You don't necessarily have to memorize those, but they're fairly obvious. Just as an example in a single subject, we always talk about y and x, right? This is for cross-sectional data where we have measurements on m subjects, and each of them we get an outcome and a covariate or a bunch of covariates, right? That xi could represent a single number, or it could be a vector of numbers. It could be age, or it could be age and socioeconomic status and height and weight, etc. Then we have the more important part, which is longitudinal indexing. And again, it becomes more important as you get more hierarchical data, because you have to represent how it varies at different levels. In this case, we have only 2 levels. We have the individual and we have the measurement within the individual. Again, I and J is arbitrary, chosen. The order I put them, I always put the highest order, the largest order unit first, but some people do the opposite, and you'll see that in the textbook. So you just have to read and know the context. But this is the way I've consistently done it. And again, as long as you define your terms in the midterm, you say, I'm doing it this way, and this is how I'm defining it. It's not wrong. It's just a different way to do it. But I appreciate if you do it this way, it makes it easier for me, but other than that. And then some kind of this is kind of basic stuff that isn't specific to this course, typically random variables. So the kind of the experiment that gets the random variables represented as a theoretical concept is capital Y and capital X. If I'm going to set them particular values and evaluate the model at those values, use small. So this is they just represent numbers, essentially. And I don't always want to put a specific number for obvious reasons. I may have a function that'll be true for any number, so I just want to put e to the minus x. I don't want to put e to the minus 1 and e to the minus 2, etc. So it just becomes very obvious why we do that. And then typically Greek letters are used for parameters. We will generalize this later when we talk about random parameters. We've already mentioned that somewhat, where we have a random intercept, or where if it's a subscript of an I, it tells you it's random. It's not a fixed thing, parameter. It's something I randomly draw from the population. So that's always true. It's a fixed. If I'm saying something that has the value of these Greek letters, but it's a subscript I, it's typically meaning that it's random. And again, this will come much more important in the mixed model section that we do next. Again, here's our main parameter of interest. We've concentrated on this. We're going to talk about other variance parameters in more detail when we get to mixed models. You all already talked about variances and covariances and correlations, but it's kind of the main parameters in the course of these. And of course, we model this with coefficients, right? But that's our fundamental parameters, the mean of y given x. And again, we have variances and covariances, right? And they have particular definitions. They're in the slides as well. One measures how variable a variable is in repeated samplings. The other one is how two variables covary, right? So I doubt this will be much of the midterm at all, but just to because I don't think it's extremely very important for this class, but only in the sense that I like to represent kind of the correlation matrices as they look, gives you some intuition, but like using proper matrix notation is not terribly important, just to know what they are. Yi, when I put yi and I define it this way, it means it's a vector of observations on the same person, right? So it's a vector. And then you could have a whole matrix of covariances, right? We talked a lot about variance, covariance matrices. I would understand what those are. And the difference, for instance, between a variance covariance matrix for coefficient estimates versus a variance covariance for outcomes conditional on x, those are separate things. We use the latter to get the former, for instance. And then if I said, if I have 3 measurements per person, on one person, draw what the correlation matrix looks like if it has equal correlation on observations. Know how to do that. Or at least know where to look it up. Yeah. Just the sort of definitions we use in the course is we have the number of independent units we call M, and the number of observations per person is Ni, right? And why do we do a subscript I? So we allow them to be different per person, right? I could have said sum of n if I assume they're all equal, but we just try to make things general. That's the whole point of notation. You want to present your notation for what you're talking about in the most general way possible that you're discussing. Then you can get more specific if you say, well, for instance, I have a study and they all had 4 measurements, right? I don't need an Ni anymore. Everyone has the same n. And the total number of observations, capital N. This is not perfect notation because sometimes people use capital N for the number of people in the target population, but in our class that's what it's going to be, just the total number of observations. So essentially, how many rows is my data when it's in long form? I already went over this. We have a modeling focus in the course. Again, we've talked a lot about just modeling the conditional mean. We can also talk about modeling the whole distribution of y, conditional distribution, where we specify something about the distribution of the error term in this case. That's normal. And that will imply what the distribution of y is, what the mean given x is, and what its variance is. So this is all derivable from that. And I said, just as I said earlier, look at the notation. Those examples at the back are probably a good guide for at least one of the questions. Notation, not that many things to really learn about the notation for this class, but you want to be able to represent things in text with notation for the kind of cases we've looked at, right? There won't be surprises in that regard. Any questions? Okay, we did a regression review, and I think this is sort of the fundamental process by which we should do it. That goes back to the roadmap I mentioned earlier, is that you define the parameter of interest. So I'm interested in the change in the mean when I change x1 by 5 and I keep x2 fixed at 4 or whatever it is. You better to pre-specify, and then you fit your model. And then once you have the model fit, you go back and you figure out, okay, what function of the coefficients do I need to get that number, right? And that's always going to be taking one model and subtracting the other, even if you're using log regression or logit regression, right? You do it at the logit scale, you subtract the two, you get the, simplifies to some function of the coefficients and some other numbers on the right side. Sometimes you can leave it as is if it's linear. If you're doing an odd logistic or log linear or Poisson, you want to exponentiate them because they have an interpretation of the log association. So it's always just comparing the linear functions first, right? You say, this is the one I want, the group, here's the comparison group. It'll just be an easy algebraic exercise to subtract those two. I get functions of the coefficients. I then, of course, would typically load that into a package. I wouldn't necessarily calculate it myself because I also want to get the standard error, and the standard error is a little harder to get. So we talked about lincom and that kind of thing. And then, so computing uncertainties, usually you don't do this. I haven't had you do this yourself, and I'm not going to for the midterm. I may ask, if I want this comparison, here's my model. Give me in terms of the coefficients and the covariates or whatever numbers I need, the odds ratio. And again, that's going to be just the exercise where you take the two groups I specify, I want it compared, and write out the model for one set of covariate values, the model for the other set of covariate values, subtract them, and then you decide, do I need to exponentiate it to get an odds ratio because it's logistic or not, right? So it's not really that hard. I mean, you have to do some algebra. I'm not actually to even solve it. You can just put one minus the other. And I'd like you to try to get the simplification, almost always beta 0 cancels out, so you don't need that on the right and things like that. But again, it's the most important thing is to be able to understand that you're comparing two means in some way. Two means on the linear scale. They could be transforms of means. And then and then by exponentiate them for the situation you do that, you put them in a more interpretable form, like a odds ratio or incident rate ratio in the case of Poisson. This is it's just examples, right? I mean, so here's the example I just said, right? I want a 1 unit change in x. I write it, so I add 1 to x here, and I keep x at there. That's the definition of a 1 unit change. Those are the mean for one and the mean for the other. I take the difference, I get beta 1. Okay, that's my estimate of the mean if I change x by 1. And again, I'm not saying what x I'm starting at because I don't have to in this linear model. It'll be the same if I'm starting x at 5 and comparing 6 to 5 or 7 to 6. It'll always be the same number, beta 1. If I have an interaction, that will change. And you'll see it just with the algebra. It'll be a function of something else. And again, I can do the same thing. This is kind of if I just have a main terms regression, just two different variables, and I want to know what happens if I change x1 by 4, keeping x2 fixed. That's, x2 is a confounder. We think of getting the unconfounded estimate association by saying, well, I'll fix it. then I know it can't be confounding. So you fix it at some value. It turns out in this case, it won't matter what it is. Little x2 could be 5, it could be 20, it could be 100, won't matter because of that linear form. And you'll just see that as the coefficients cancel out. This term cancels out on both sides, right? So again, it's just the same principle over and over again. And this is where you have that little slight complication where you say, I'm going to keep x2 fixed at some value. I want to know what the change to x4 is, but I have this term now. And so there's just another term I have to put on both sides of the equation. Without doing that, you can easily see I get 4b1, 4 times x2 times b3. So I have to specify what x2 is in order to actually get a number there. And that's what interactions do. If the variable of interest has another term that's an interaction, and that could even be like a polynomial term, which is like an interaction with itself, it means that the association that you're going to get is going to be a function of that other variable. So that's a general rule you can use if you want to think it that way. But I don't like general rules here. I just like doing the mindless process of writing down the mean at one, writing down the mean at the other, and subtracting them.
So what would be the kind of question for addressing this specific aspect of the...
It would be something like this. I could say, okay, here's my data situation. I fit this model, and I give you the output in R. And then I say, write in terms of the algebra. You don't have to, again, calculate it in the end. And you don't necessarily have to use the betas now. You could just use the betas it estimates, just the number. I could say, give me the odds ratio for forward unit change in age keeping cholesterol fixed. That would be an example. Practice that. I just think that's a really good skill. Generally, if you're going to do regressions as part of your research, that's just a good skill to have because that's generally what we're interested in, right? Prediction's rare. Prediction, we don't care about the form. We're just trying to get some combination of covariances as a best job predicting. We're not trying to interpret anything. We don't measure association and pure prediction. We don't do a lot of that, right, in public health. It's often, we do some, but for the most part, we're doing how is this related to the outcome? What's its impact on the outcome? Does its impact vary as a function of some other variable? Does the impact change based on what you start at? Like is a 4-unit increase always going to give you the same odds ratio, even if I don't have interaction? Those are kinds of things we're interested in.
And the answer would be like showing this model and then that you have to subtract and then just the final 4 times B1.
Yeah, in other words, if I had B1 was equal to 2.5 in my output, you would just say 4 times 2.5. If you put 4 B1, I prefer you actually use the output in that case. And I some ways don't even have to give you the model. I can just give you the output. That tells you what the model is, right?
Yeah. So you don't necessarily want us to like write a model with all the coefficients and then show this.
Yeah, you can skip writing down the coefficients notation like a beta 1. You can just put, if you want to write down the model first, you can just write down the numbers. Okay. 1.5 times beta 1.
Yeah.
Whatever. No, I'm sorry, 5.1 times x1, whatever the betas are. Again, I'm just trying to see if you get the concept. I'm not trying to find, be technical. You didn't quite get the right answer because you didn't fill in this. That's not important to me because you won't remember anyway or you won't care. I want you to get the concepts. We talked about logistic regression. Again, there's nothing new to learn about any of the regressions. And even with Cox regression, they all have the same form. They're all transforms in the mean are equal to some linear function. And so when we compare two groups, we compare them on the linear scale, and then maybe we have to exponentiate them afterwards, depending on what kind of model we're doing. That's it. So logistic regression is no different in that regard. It's exactly the same. Again, except for if I ask for the odds ratio and not the log odds ratio, which is what the coefficient scale, the linear scale will be, you just have to exponentiate, right? You just have to remember that. Yeah, and this is basically what I just talked about. So again, this chapter 3 follows us for the rest of the course. It's already followed us into the GE, and it'll get more, when we start getting more complicated models. And we'll do a lot of examples. We'll do some more GE examples. We'll do a lot of examples and mixed models in class because it's more complicated to specify the model and it requires more interpretation. But this just general way skills on how to fit and how to interpret and how to use coefficients for reporting associations of interest is just something that will always follow you. Won't need a calculator. Just to emphasize that again. So I only have one slide for graphical representations. So imagine, I would think of a problem like this. I could say, okay, I have 5,000 patients measured irregularly over time, average of this many measurements, and I want to make a spaghetti plot, but I want you to make it so I'm able to see the not just a cloud of lines, but specific. I'll be able to look at patterns, individual lines within that. How would you subset, and what would the plot look like? I'll just have you draw a schematic plot for this kind of thing. So it's these kinds of questions. Again, I also could add, and I think this is relatively fair, but you tell me if it's not. I could add ggplot kind of code. It'll give you what the data means and everything. Code, and I can say, what is this plot going to look like? Of course, you don't know the slopes or anything. You just know it's going to be a plot of smooths, or it's going to be a spaghetti plot connecting the dots, or it's going to look like I won't make you draw a heat map, but that's another, that would take too long, but that kind of stuff. So again, it's not tricky. It's going to be using things we talked about in class, but just, and other ideas that we did at the end, the last, there's 3 parts of this lecture. The last part was how do you make plots that separate the longitudinal from the cross-sectional effect, which isn't complicated. We look at the change of one versus the change of the other. I just gave you the answer for that, but that's a reasonable question to ask. How would I do that? And you just describe it. I'm not going to have you write code, right? I'm not going to say write the code out for ggplot because that to me is pointless. But I could have ggplot, and you should be able to reason what that's going to look like. So again, I don't want you to memorize all the possible features it could have. It's just the general idea that this kind of plot's going to give you something that looks like this, and it's going to capture these kind of patterns. Features of longitudinal data. So this is just that sort of where we go back, okay, what are the things we have to learn to understand longitudinal data that's good about it and complicated about it? And of course, the big thing we've been talking a lot in GE is dependence, the fact that you have repeated measures on a subject and you can no longer assume they're independent when we do our regressions and get our inference, right? So because, the variance, you can think of trying to get an average. I'm going to get an average of all the observations. I can't assume that they're all independent because I've got this term here. So if I have a variance of a sum here, the variance is equal to the variance of the first and the variance of the second, plus 2 times, this is wrong, 2 times the covariance between the two. So basically you characterize the measurements on the subject if you're talking about variance in a variance covariance matrix. That symmetric matrix where the diagonals are the variances of each of the outcomes, y1, y2, y3, and the off diagonals give you, by the indexing, where the first column is observation 1 and second is columns observation 2 to observation n, and likewise on the rows, that each of them gives you the covariances between those 2 observations, right? And again, we can represent that generally, just putting in variance of this and covariance of these 2, or we can start modeling it by putting something else that says, oh, I'm going to assume they all have the same variance, so I can replace that middle variances, the variance of yi1 and yi2 by sigma squared, for instance, if they all have the same thing. So be able to translate, like I tell you the model that I'm assuming the covariances, let's say, the variance covariance is on a subject, you should be able to use notation. It doesn't have to be unique. Everyone doesn't have the same notation. It's just to be consistent. That gives me what it should look like, right? So I'm replacing just the generic name of the parameter to a specific model, which could be like sigma or rho or that kind of thing. Anyway, the general assumption is this. We've talked about this. The general assumption is you don't want to assume independence because you know you can be biased at least. If I allow for this dependence, particularly when I'm getting my inference of standard errors, even if they are dependent, it's still the right model. Any model I fit that's bigger than the true model is still the right model, as long as my model is within inside of it. So if I assume absolutely, if I assume that they have equal correlation, but they're uncorrelated, well, that's within equal correlation. Equal correlation is also zero. They're all zero, and that's independence, right? So that's the way to think about it. You always do a better job in terms of bias within the standard error by assuming a bigger and bigger model for your variance covariance. And that's why in the end, when we get to GE looking forward, when we get that, we assume nothing about the correlation structure. We just estimate it completely based on individual residuals. Then we talked about, this is just an example of how, like, let's say I had a little causal diagram, yi1 and yi2, and then I had an ei1 going here and an ei2 going here, and then I had some unmeasured thing, alpha I, that goes to both of them. So this right here creates that correlation, and you can show what the actual correlation is. It's the variance of the alpha I divided by the total variance was the alpha I variance plus the variance of the residual Eij. So this is looking forward to a model that would imply correlation. GE, we don't worry about models. We just say there's correlation. Guess what it is when we estimate it, and after we guess what it is, unguess that when we get our inference and assume nothing, right? When we get to mixed models, we'll make very specific models of the correlation. Will be a function of these terms that we put in our model, which are going to be random things. And if you share some random variable, two observations share a random variable, they'll be correlated. That's a general rule you can rely on. So both of these share alpha I. That means they're going to be correlated. Now, if I condition on alpha I, if I observed it, they'd no longer be correlated. If they're given alpha I, they're no longer correlated. They're independent. If I block these pathways here. But because we can't condition on it, we don't know it, right? So there will be correlation in our data. And we can't get conditional independence anymore because we don't measure the alpha I. It's just part of our latent variable model. And latent variable models are weird. They're used all the time. They can be very useful, but they're odd, right? You're adding essentially like covariates that you don't observe to try to explain the variance. So I always feel a little uncomfortable. Like I just want to stick to the data, estimate things based on what I know. Every time you enter latent variables, you have to rely on assumptions. There's no way to identify parameters unless you say something about their distributions and stuff. But they're very commonly used. They can be useful. They can be used as a proxy to get other things that we'll talk about, like what's the variance of different levels and things like that, different hierarchical levels, but in general. You might want to remember that in a model like this, simple model, we call the variance of the alpha the between subject variance, because if I could have an alpha I prime, right? So I have a yi prime 1 and a yi prime 2, and then the ei prime 2 and the ei prime 1 goes there. So the variance between people is defined by the variance of this thing. Those are the things that differ between people, right? That's the between person variance. And the within person variance, so the difference between these things, which is within a person, is this error term, right? So that defines the within person variability. So, sorry about that. Let's see, a little bit of this. We did this example. We said, okay, we assumed that model, and we if we assume that was a true model, but then we ignore that and say all the observations on subjects, even if they're on the same subjects, are independent, and we estimate the variance based on that model, what is the expectation of that variance estimate? That's just the sample variance. If I have 5 observations on 20 people, that's 100 observations. How would I get the sample variance? I take the sample variance of those 20, and then I would divide by the sample size would be 100. Take the square root of that, and that would be my standard error. That would be naive. That would be assuming independence, right? We've talked about naive standard errors versus robust. Where's the first time it came in? So this is a naive standard error for just an average. It's actually, in this case, it's not the standard error. It's actually standard deviation. It would be the true value of the parameter as sample size goes to infinity. So it's the naive standard for y bar, where I can show that the true variance of y bar is equal to this, and you can see these things aren't equal. So if I use sample variance, it's going to be equal to that thing as sample size gets bigger and bigger, but it should be equal to this thing, and of course they're not equal. So it means I'll have this is just a simple mathematical way to show, yeah, your standard errors will be biased if you ignore correlation in this context. In this context, you're assuming almost like you have too big of a sample size. In this particular model, you have functionally less information than the total number of observations because of that correlation between them. And so you can show it, obviously this is the case. So you're always going to be underestimating the true variance, true standard error, true standard deviation of the parameter estimate y bar by using the sample variance, assuming independence. And it'll be biased downward. That's not always the case. We already saw cases where you can also be biased high by ignoring the correlations. So in some models this will be true. In other models it will not be true. It will be the opposite. And it's easy to show that too. Easy. I mean, you can show that mathematically too, based on that. I'm not going to ask you for that at the exam, but that's something I could show later if it's of interest. So I tried to get some idea. Well, never mind. So that was one of the things. It's complicated in terms of inference mainly, that we have to account for the correlation in order to get standard errors that won't be biased, either high or low. Now, there's a lot of, I messed up the numbering, but it doesn't matter. So there's a lot of advantages to longitudinal data, which are sort of, many of them are intuitive, some are less so. I mean, one is, of course, I can look at cause and effect now in time. I can look at time ordering. I can measure something at one time and say, did it have effect on something I measured the next time? And I know it preceded it, right? So I don't have that issue with longitudinal data, well, cross-sectional data, where I may measure 2 things at the same time, and I don't know what came first, particularly if it's like self-reported or whatever. So it gives you the ability to have this causal ordering, because one principle of causality is the thing that causes the present can't come in the future. That's built into how we build these models and assume things. So that's one thing you get. The other one is, of course, if I only measure something at one time, I can't get lagged. I mean, I suppose you could have a study which says, tell me your outcome today and tell me your exposure 4 days ago in a cross-sectional way. But besides that, if I'm measuring everything on the same day for a subject, I can't put in what was the history of that exposure, because I only get it at one time. So it allows you to get more interesting associations of not just something that happened at the same time, but maybe some things that happened in the past. It's like when you think of life course, the importance of life course when they talk about looking at outcomes as an adult, and you want to look at the trajectory of your exposures as a child, right? This is good. Obviously, can't do that if I just measure proof in one time. I don't get all those other events that occurred in the past. I get current measures of SES or other things. So that's an obvious advantage. That I can look at the effect of childhood on childhood stress or childhood traumatic events on adult, let's say, mental health, things like that, right? And longitudinal studies are super important for those kind of questions. Again, you can do you can make a kind of a pseudo longitudinal data set by saying, I'm going to ask it. I only get to collect data once, but I'll ask about the past. It's really constructing a longitudinal data set more than prospectively collecting it. And, we would sort of evaluate it the same way, but it probably has less validity than if I actually measure things when they occur. What I call 4 and 5 are kind of are very similar in some ways. So you can argue that if I may have all these pathways from things I don't measure that are fixed for a person, but go through previous things I do measure. And if I adjust for those, I block the confounding effect for stable things, even if I don't measure them. And you could I drew little causal diagrams that showed this. So for instance, when I'm looking at exposure versus an outcome, and I want to adjust for all these other factors, well, I can use the outcome the previous time. But that's certainly anything that comes to my current outcome has to come through my past outcome. Maybe it always has to, all of it has to come. There's no other independent pathway. It only affects my current health state by what it was in the last health state. That's an assumption. It could have another pathway into the current health state, but your hope is that you have enough of a history of a subject you can adjust for that you can get rid of confounders that you didn't even measure, the ones that are fixed and stable on the subject. And that's a huge advantage for longitudinal data. The fact that you can adjust for the past, including past outcomes, make one's argument that I'm getting rid of confounding much stronger than if I don't have that information, because it's not longitudinal. Anyway, you can make this just arbitrary list, but you can make this, ad infinitum. It could be a long list of things that you just aren't able to measure, but you don't want them to confound a relationship of something that's time dependent and the outcome. You might be able to use the past and say, well, the only way that's going to affect the current outcome is through the past outcome. And if you can make that argument, it's an argument. It's a certain causal model. Then you can argue that longitudinal data will allow you to get an unconfounded estimate of the association of a time variant thing, adjusting for the history. This is just one specific example of that where I have this. It's mainly like how people come to a study and what their first measurement is relative to the explanatory variable. We can think of it as time, this kind of thing. I'll just do the diagram. So no, I didn't do that right. I could have done it the other way, but it's fine. So this is my data. If I just do a regression, just like I put the current value of exposure versus the current value of the outcome, the current value of X versus the outcome. So this is Xij, Yij. You get a line that looks like that, maybe. Well, actually, what am I saying? No, that's totally wrong. You get a line that looks like that, right? If I only got one measure per subject, when the truth is they're connected this way. So the true relationship of Yij and Xij is it increases over time. As Xij goes up, Yij goes up. So if I had cross-sectional data and I just did a standard cross-sectional analysis, which would just be this, right? I would just be modeling Xij versus Yij versus Xij is beta 0 plus beta 1. Xij, that gives me the red line. And of course, that's misleading, right? And we don't know how this confounding necessarily occurred, but it occurs like how they enter somehow is confounded with their value of X. Their relationship with X and Y, for instance, determines when they enter the study. That's just, you come up with other examples, but this is sort of a classic way that longitudinal data, by adjusting for X1, so that's a history, goes back to that general story, allows you to estimate both the cross-sectional effect, that's the red, and also the blue one. where this one will not do that. And so again, I think it's better to think of, I mean, this is a particular example where for this type of, simple bivariate relationship where you can show it in a graph and you can provide a model that can distinguish these two. And of course, we're almost always interested in the blue one. I mean, it might be interesting why do people who start later with Xij have a lower Yij? That could be an interesting question. I don't know. I just made it up. But even if I don't care about why that's happening, that doesn't look as interesting. What I really want to know is this relationship. So you have to make sure you're using the past to adjust to get rid of that confounding. In this case, how they enter the study is related to the outcome. At what point, if this is time, for instance. So if I gave you a plot like this, I said, okay, what's the, here are the points, here how they're connected within people, draw on this plot and give me this model here. Draw on the plot, what's the line, what's the slope for BC and what's the slope for BL? A little bit of a nonsense question, but I mean, just so you understand the distinction between the two patterns and the fact that I can't, this is where longitudinal data people often mess up, like in student projects. They don't at all adjust for the history at all, and they end up getting the cross-sectional effect when they could have really gotten a much more compelling, unconfounded effect by adjusting some way for history. And so it's one of the common mistakes people often do, is they don't use the richness of the longitudinal data to try to separate out what they're really interested in. So that's an example. And if it was a take-home, I'd have you measure those lines in a grid and give me the actual numbers, but I'm not going to do that here. So that's a related. So this is related to the previous one. It's related to 4 that I just talked about. Make a good use of the history in the adjustment set. Again, if you have hierarchical data, so I can, again, what does this imply? This implies there's some parameter beta 0, it's the grand mean, and then there's a random variable that happens at the level I, village, one that happens at the level ij, which is person within village, and eij, k, which is measurement within person within village. You can use this. If you assume this model, I can get a variance decomposition. So it's almost like a game. Like, I don't know if this model is true, but it does allow me to, if I specify it, to estimate the variance as due to the village. How much does that contribute to the total variance? How much does the individual contribute to the total variance, individual within village, and how much does time with an individual within village contribute? This is a mixed model. I wouldn't worry about this for the midterm if you don't want to, because we'll come back to that. But I just wanted in this lecture, because it's another thing that makes longitudinal data, or really just in general hierarchical data, useful, is that you can, before you even collect covariates, you can say, well, if I was going to go here to study something, the village looks like it contributes the most variance, so it's the village level that I should be concentrating on. And this is kind of this is more complicated. We learn when we start thinking about unbalanced data in GE, but in general, ignoring correlation doesn't necessarily give you bad estimates. I could just say put it in the standard regression procedure, but it always will give you biased inference. So that's why it could be totally legitimate to fit a logistic regression where you don't have any working correlation, just independence, but then adjust the standard errors for the possible dependence afterwards. That may be a perfectly fine estimate, like we've seen where that's no different from doing exchangeable because the data is balanced, right? So it's not, it's basically the biggest harm to inference is not so much the estimates ignoring the correlations, often the variance estimates that ignore the correlation, the variance of the coefficients, standard errors. Okay, then we did lecture 6, which is baseline covariates. And again, this is done just for practical purposes that I don't always need to keep the data in longitudinal form if I have repeated measures of the outcome, but a single, like just baseline covariates, because they're not changing over time. So I can't look at change in them versus change in the outcome. So in that way, I can just convert all those measurements on the outcomes over time into a number, treat that as my outcome. So I have one outcome per subject now, and I can do standard regression. That's really the bottom line of most of this lecture is like, if I have a randomized trial and I am randomizing some intervention at baseline and placebo or no intervention and following the subject regularly over time, I could treat like repeated measures but you don't have to. You could do something quite simple, which is like take the average of the outcomes or take the trend and treat that as the outcome. And just do a comparison of treatment and intervention on the slope, if it's something that has to do with growth, for instance, or if it, as we discuss in more detail, if it's just a count, you just count the number of events, that's a new outcome account. And that's the only reason to talk about Poisson and negative binary regression, except the fact it's just useful things to know in general, is if I have repeated binary outcomes and a fixed baseline covariates, you can summarize the count, and then you want a regression that is proper for counts, which is like Poisson, log linear regression. And then, so we talked about that. We talked about the Poisson distribution. And I might remember this. I mean, again, it's a little bit silly, but I could ask a question about the relationship of variance and the mean for Poisson, right? And again, if lambda x is some linear function of other things, beta 1x, then the mean of y given x is lambda x, and the variance of y given x is lambda x, right? Because ultimately, we're doing it to model the mean as a function of covariates, again, like we're always doing. And so that's what it implies. So in this case, it's just I don't have covariates, it's just a marginal mean, but we're typically talking about the mean as a function of x. And in that case, the variance and the mean are equal when you condition on x. Then we got to the more relevant thing. Again, it's a log linear model, so the log of e of y given x is beta 0 plus beta 1x. I have the linear part here, and I have the h is a log now, the length function. So again, if I wanted to compare the mean at two different levels, I do it at the log scale first. If x increases by 4 versus stays at x originally, I take the two linear functions, subtract them from each other, get the function of the coefficient on the right, and then of course you want to exponentiate it, because in this case, beta 1 is the log of the mean ratio. Sometimes kind of a log of the IRR. If I exponentiate beta 1, that's the incident rate ratio. So it's just, again, that's just lambda 1 over lambda 0. That log or logit structure means that the parameters of interest are going to be exponentiated coefficients. We talked about how in the Poisson model to handle the fact that maybe I'm following subjects different amounts of time when I'm summarizing their binary events as a count, and I want to incorporate that and also in my model, because it's not fair to look at the number of events of somebody that reports diarrhea 10 days or reports whether or not they had diarrhea in 10 days versus 100 days. You don't want to treat those counts equally. And if you're assuming Poisson, it turns out I can do that by just taking the amount of time they're followed and multiplying it by lambda. So basically, lambda of t x is t times lambda 1x. So it's just t times the mean for one unit of time, or one unit, in this case, could be a day, per unit day. Again, you don't have to do that. Like, we didn't talk about this, but you could just go, I could model this as e to the beta 0 plus beta 1 x plus beta 2 log of t. Where I actually don't assume that it has coefficient 1, because that's essentially what this is. This is just a covariate, but it's assuming the coefficient is 1. I could estimate it. That's a bigger model. That's probably going to give me a better answer in some sense, because it's bigger than the one where I assume it's 1. But that's not strictly Poisson, something else. Let me just... Don't worry about this. Okay, then negative binomial. So again, this gets us, we talk a lot about inference and robust inference versus naive inference is a big part of this course. And this is just an example of that, where the Poisson, when it does maximal likelihood Poisson, it's going to assume the mean variance model are true, particularly, and that variance model factors in when it estimates the standard error. And that's a big assumption, that the variance is equal to the mean. So the negative binomial is a bigger model. It says, well, it's the variance, it's the mean plus this mean squared over the dispersion parameter. It can be equal to the mean if the dispersion parameter is infinity. So it contains the Poisson model. It's a bigger model, and therefore it's more likely to get better standard errors. And again, as I mentioned, you still are modeling the mean. So like all the parameters have the same interpretation, like log, incident rate ratios or ratios of means. And yeah, so, if I had practical advice, it was like just fit negative binomial. I mean, why bother with Poisson? It's only one additional parameter, and it's more likely to give you more accurate inference, particularly if, in fact, you have more variability among your people than Poisson, which is often the case. And remember, we talked about how the motivated negative binomial is a mixture of Poissons. Everybody in the population has their own Poisson, their own lambda, and that lambda comes from a certain distribution, and that will add that result, which is gamma. If you assume it's gamma, it's just some arbitrary distribution, but you convolve the Poissons with the gamma, and you get the negative binomial. So you can think of it as a mixture of Poissons. And because it's a mixture, it has more person-to-person variability, it just means the variability will be assumed to be greater. Again, Poisson's a submodel, so if your data really fits Poisson well, that dispersion parameter will get big and it will fit just like Poisson. So it doesn't hurt you by fitting it, essentially. If you had to add 500 parameters or something to make it that flexible, yeah, then you might be overfitting, right? But if I only have one additional parameter, there's no additional overfitting, essentially. And so there's no risk to doing this. It's what you should do. I just talked about this, so this is definitely true. Over-dispersion just means that the variance is bigger than the mean. That's all it means in this case. And of course, we talked about the negative binomial. And this is just sort of summaries of this thing. So again, you can use what are called offsets. Remember, offsets are just special covariates you enter that have slope 1. That's the definition of an offset. So if I want to add something to my regression, but I don't want to estimate a coefficient in front of it, that's an offset. So in this case, if I put the log of the time that a person has been followed, that is an offset you would use for Poisson. So basically, the bottom line is we didn't discuss how to do this with Poisson yet, but you could take Poisson regression and just use the estimates, but then get your inference assuming no longer Poisson, doing robust inference. So estimating the variance empirically, like we did in that example at the end of GEE. And that would be okay, right? Because then I'm using Poisson for my estimation, but I'm not using it to get my standard errors. I throw out that assumption. It's very similar to what we do in GE. You can do that also with cross-sectional data, right? I can fit a linear regression, get my estimates, but then no longer assume constant variance when I get my standard error. And that's what's called the sandwich estimator for the standard error. Always best practice. Never the default, and not typically reported as the default, but it always should be. It's just one of these inherent flaws that most statistics is taught in a way where you're assuming the model is correct. But we shouldn't do that when we have every reason to believe the model is not correct and we still want accurate inference. And so, so you can either use negative binomial is still considered naive in that it's assuming something, right? It's assuming a model for the variance. So I can get more robust by just assuming nothing. And because of that reweighting thing we talked about, GD, negative binomial can give you different estimates, right? Because it's going to reweight the data differently depending on what the predicted value for that observation is. So you get different weights for observations than you do with Poisson. So it's a different variance, and they can reweight things somewhat as well. So again, it has that same feel we talked about in the case of unbalanced data. The balance doesn't matter here because we only have one observation per person, but that principle still applies. Okay, and then the last chapter, GE, again, we're just doing regression, but we're now accounting for the correlation both potentially in the estimation phase and in the inference standard error phase, but we're doing them differently for both phases. That's the kind of thing to remember, right? So again, we're just modeling the mean, some function of this. I should put H, because I've used H before. H. We haven't, no. So, yeah, it could be this. So it shouldn't be this. It should take away this. I don't like that. Say is equal to some H of E Yij given Xij. So it's just some, again, we only looked at 3. H is nothing, just the identity. It's the logit, it's the log. So I'll just put H. I'm just being consistent there. Sorry about that. I don't know why I shifted. And then so what it does is it models the mean structure using some working correlation, and we talked about how that matters and when it matters and when it doesn't matter. And when it does matter quite a bit, we're in a much more complicated world, because that implies really two different parameters, and I gave heuristics about how to choose one working correlation in that context, but that's all it is. It's not rigorous. And tried to give you some feel for how it works. So this is the estimating equation it's solving. It has to solve mathematically the estimating equation to get its estimates of beta. So it sets up these, which are the same estimating equations that you would motivate by maximum likelihood. But then the difference is we're not using them, we're not estimating the whole likelihood because we're not specifying anything about how the y's are related to each other, the same outcomes within a person. We're only estimating the marginal mean of the mean of y given xij we put in there. But we can still get consistent estimates, like I said before. You can ignore, in linear regression, I can get consistent estimates of coefficients regardless of my error term is normal or not. That's an additional assumption you don't really need. But to derive the likelihood function for it, I have to assume something about the errors, and normality is typically assumed, but that gives you a estimating equation that will work whether it's normal or not. And that's similar here. So I'm using the form of the estimating equation from maximum likelihood that I went over in the first few slides in this chapter, and you get something like this, but it means it's a function of this inverse of the variance covariance of the outcome, and I have to put something in there, right? And that's where the working correlation comes in. So working correlation is plugged into this. So how is it plugged in, or what do you assume? Again, this doesn't say anything. It just says, okay, here's an example of the variance covariance of observations on one subject conditional in their matrix of predictors. So it captures the within person. Well, this makes no sense. It's just the variance covariance of one subject. Now it builds the variance model by assuming the variance model of the family, right? That's always an assumption. So it says G is not fully robust. It's semi-robust, meaning if it's plus, you put Poisson, it's going to assume Poisson variance. So the diagonal elements of the variance covariance are determined by the model. The off diagonals are a function of the model for the mean, but also the correlation model. And that's the one where you have to put in some working form for it to build that V inverse that it can use as weights in that regression. And this is just some examples. I could assume independence, right? I could assume compound, well, we call it exchangeable. It used to be called compound similar, just take that out, which is that everything is equally correlated. In this case, I'm just trying to guess something that may be able to get more efficiency by choosing something closer to the truth. As I said, even if I use independence versus exchangeable, it's not going to matter if data is balanced anyway. It has no effect. If I maybe my data is more autoregressive, so things that are farther apart are less correlated. If I use that, I might get a little more efficiency if I have balanced data. And my mean model is correct. But again, my basic message was if your data is balanced, it doesn't matter what you choose if it's the working correlation. It's not going to affect much. And this is what autoregressive looks like. Just as you get, these numbers are less than 1. As you get farther away, they get smaller and smaller if I raise them to a higher power. And again, some of these are available for any type of data, balanced or unbalanced. Some are really only available for balanced data. This is one of them. I need every person to have 10 observations or so, something like that. So again, if the mean model is correct, the different working correlations give the same coefficients asymptotically. Sometimes they'll give you exact coefficients. And this is even if data is unbalanced. Even if data is unbalanced. So again, if you get the right model, it doesn't, if I have a line here, or I find a curve, well, let's say a line, and I weight some things higher than lower, but the model is correct, it's still going to go to this same line. It's when the model is not correct that you start getting different estimates based on the weights, and that's an important thing to remember. That's in that, I go over that with the plot in there. So again, if the data is unbalanced, it doesn't matter if your mean model is right, that all the working correlations will go to the same numbers asymptotically as sample size gets bigger and bigger. There may be finite sample differences, but they'll all do that. And if you choose a correlation model that's closer to the truth, like maybe it's more like unstructured is the truth, you might get smaller standard errors. Real small, not like bias standard small, but small standard errors, truthful. But basically, this is my bottom line, is for balanced data. So when balanced data is the case and the model's wrong, that's where you can start getting really different answers when you have different working correlations, and because of that whole reweighting thing. And again, you can see that here. If I do something where the model's wrong, so here's the truth, here's my data. Actually, let's do this. And these are the weights, how big my circle is. If my weights are high here and I fit a line through this, it's going to go like that, right? Those will dominate. If I have another one where the weights are higher down here, so the same plot, but these are bigger, it's going to look more like it's going to look more like that. More like the lower part of that curve is going to dominate. So in other words, if the model is wrong, the weights will affect what you're estimating. Are you estimating something that's dominated by the lower portion of the curve or the upper part of the curve? And it gets more complicated when you have multiple dimensions, multiple covariates. But that's the basic idea. And again, as I gave the sort of rule of thumb that if they're very different, your coefficient estimates in unbalanced data, when you're comparing exchangeable and independence, really the only two things you can fit anyway for working correlation, probably better to use exchangeable because it makes it more like people have equal weights rather than observations have equal weights. But again, one can come up with counter situations to that. So again, I make, to end, I would say like I could give you like two outputs and I can tell you, so, okay, here's what I got. Describe something about the data that you would expect from these output. And that's something that I might expect you to know. Like, oh, here's a situation where the standard error is, the estimates are identical in the independence versus exchangeable. And the standard error naive for the exchangeable is equal to the standard error robust for exchangeable. Can you tell me about the underlying data, something about it? So much like I went over in those things, I'll have one question like that. All right, any final questions? Well, I can't believe I got through that. Because I could have just had one lecture. Yeah.
So do you think like reviewing the lab, because the lab also had like similar questions like what you're talking about, but just like even like reviewing like the lab questions, that would be helpful.
What would be helpful?
Oh, preparing for the midterm.
Oh yeah, it would be.
Yeah.
Yeah. I mean, I'm looking at both the lectures. I'm looking at the labs. There's a lot of overlap with those two. There's some differences, but a lot of overlap. So there's not many things that are only in the lab, but there may be a few things. I'm concentrating more in the lecture. If you find a thing in the lab that we didn't discuss at all here, don't worry about that. And yeah, and then if I come up with a question that's maybe the answer is debatable, put the answer you think is best and tell me it's debatable. Like we're all adults here. I mean, I think tests are good in that they coerce you to kind of learn the material a little bit better. It's the only reason they're good. But in the end, I just want you to learn it. I don't care about the grades. So, okay. I know that's easy for me to say.